Hi, welcome to module 4 of Weekend's lecture. So till now we have seen some basics of Boolean logic and the basics of operating Boolean expressions and so on. We will now start looking at more machinery required to start from a problem, how to get a truth table, how to get to an expression, and from there on how to minimize. So to do that we need a few things. So this lecture is going to be slightly theoretical in nature. We will not be looking at too many problems. There are lots of definitions and other things that you have to know, so that from the next week onwards we will know all the terminology that we need to. So the first thing I want you to know is a change in notation that we are going to have. So far we have been using this dot for and everywhere, but using it everywhere is quite laborious because we will have to remember to put the dot everywhere, and visually it is not very good. So for example, if I go and look at this expression here, x1 complement and x2 complement, or x1 complement and x2 and or x1 and x2. So this is a bit tedious to do every time, and in basic algebra we don't always put this multiplication everywhere. So just like that we want to be able to get rid of this dot whenever possible. So this is the same expression rewritten with and removed. So x1 complement and x2 complement. So the and is implicit here. Whenever we write something of this form, the and is implicit. So x1 complement and x2 complement, or x1 complement and x2, or x1 and x2. So this is visually better than doing this, and especially if you are going to write a much larger expression with many terms and many variables, remembering to put that and is a problem, and also it becomes visually slightly more clunky. So instead we would drop the dot if the intention is clear. So you will have to remember about usual precedence rules. So whenever there is, if you have a plus and an expression which has an implied dot or a dot, you have to be careful about the precedences. So in basic algebra, if you have 5x plus 3y, you would interpret that as 5x added with 3y, right, and not 5 times x plus 3 times y and so on. So the same rule applies here. When you read this expression, this is x1 complement and x2 complement logically ORed with x1 complement and x2. It is not x1 complement and x2 complement or x1 complement. So you have to be careful about how these things are grouped. Sometimes we will use parentheses explicitly, sometimes you should use the basic rules of precedence that you have in algebra, just carry it over here. Okay. So now let us move on to some definitions. These are fairly simple definitions, but these are necessary so that whatever we discuss later becomes clearer. So we will start with a single variable or a literal. So a literal is essentially a variable which is either in the complemented or in the uncomplemented form. So let us look at these examples here. If I have a, it is a single variable and it is in the uncomplemented form, a bar is in the complemented form. So a and a bar are actually two different literals of the same variable a. So you use the variable a and a bar are two different literals. This expression here, a bar plus cd, is not a literal because it is not a single variable in the complemented or uncomplemented form. It is a combination of multiple variables. So this is not a literal. So single variable either in complemented or uncomplemented form gives you the literal. A product term is essentially either a single literal by itself or a logical product or and of two or more literals. So we will start using the, so instead of saying and every time, we can start using the term product now, because it is just like multiplication, right. So I told you the analogy earlier that you can think of and as multiplication. So we say product of two terms, product of two expressions and so on in the integer and real number fields. The same thing we can use it in, same terminology we can use in Boolean algebra. We will use the term product for and a product term is either a single literal like this. So a bar are single literals, so they are by definition product terms also. So product term includes literals, or you should have something of this kind. So AC is actually a and c, so it is a product of a and c. A bar cd is the product of a bar, c and d, and so on. Even this is a product term, a bar b is a product term. A bar plus cd is not a product term because this involves a plus here. So this is not a product term because there is a plus symbol here. It means this a bar or cd. You cannot rewrite this using only single literals and their products. So all these are product terms, this is not a product term. Similarly, a sum term is a single literal or a logical sum of two or more literals. So a bar, a plus c, so this is a logical OR of two literals, this is a logical OR of three literals and so on. So these are all valid sum terms, and a bar plus cd is not a valid sum term because it has a bar plus cd, and this is not a single literal. So if I had given you a bar plus c, that is okay, that is actually a sum term, but a bar plus cd actually involves a product also. So a product term should not involve sums and a sum term should not involve products. So now let us go and look at what a normal term is. So a normal term is usually a product term in which no variables appear more than once. So let us look at this. A is a literal, it is actually a sum term as well as a product term, and there is nothing repeating in it. So it is a normal term. Similarly, a bar. A plus c is you have a single literal with a plus in between. You do not see any variable which is repeating more than once in each of the terms. So a plus c is a valid normal term, a bar cd is also a valid normal term. So a normal term is either a product or a sum term in which variables appear no more than once. So if you go and look at this, you have a bar plus a, right. So you have if you take this as a sum, right, a bar plus a is the same variable appearing twice, so it is not a normal term. Similarly, earlier I showed you this a bar b, right, it is the same variable appearing twice in the uncomplemented form and once in the complemented form, so this is not a normal term. So a normal term is a product or sum in which no variable appears more than once. Even if it is complemented and uncomplemented form like this, a bar a, it is not a valid normal term. Now what we really need is the definition of minterms and maxterms. These are the things that we need. So a minterm is defined on n variables, it is a normal product term. So let us see what that means. Let us start with normal. Normal means it can, so let us start with product. Product means it should be a concatenation, a logical AND of n variables, right. We want n literals and we want n of them to be concatenated and it should be normal, right. So let us see examples. So a bar bc, right, it has, so if I say that a bar bc is a 3 variable minterm on a, b and c, let us see why a bar bc is a minterm. So first of all, if I say that it is a 3 variable term, I should have 3 variables in it. So I have a, b and c, so these are 3 variables. And what are the literal forms? A is in its complemented form a bar, so that is a literal, b is another literal and c is another literal. And I have a product of these 3, so it takes care of product part of it, and finally it is normal because none of a, b or c is appearing more than once. So a bar bc is a minterm, abc is also a minterm. A bar b cannot be a 3 variable minterm because a 3 variable minterm should contain 3 variables. A bar b contains only 2 variables, even though it is a product of literal a bar and literal b. So it is a valid product term, it is a valid normal term also, but it is not a valid 3 variable minterm, it is a valid 2 variable minterm however. Similarly, a max term on n variables is a normal sum term with n literals. So this definition that it has to, if it is a max term of n variables, it should have n literals. Similarly, a minterm on n variables should have n literals. So let us look at 3 variable max terms. For example, a bar plus b plus c has, first of all, it is a sum term because it has only sum between different literals and the literals do not repeat and all the variables appear at least once. In fact, all the variables appear exactly once. A appears as a bar, b appears as b itself, variable c appears as a literal c itself. So a bar plus b plus c is a valid max term. A plus b plus c is also a valid max term in 3 variables. Like here, a bar plus c cannot be a valid max term in 3 variables because it needs one more variable, whereas a bar plus b is a valid 2 variable max term. Now let us move one step further. a sum of products, also called SOP, is a set of product terms, which means it is a collection of terms that are connected with logical OR. So, let us parse this sentence, sum of products. What do we know about products? The product terms will only have and in between them, right. So, if I have a product term of n literals, I will have only and connecting those, and a sum of products should be a summation of product terms. So, let us go and look at this. So, let us start with this expression first, a bar c plus BDE. A bar c is a valid product term, BDE is a valid product term. So, a bar c plus BDE is sum of products, so it is a valid SOP. Similarly, AB plus C, so this is a product term and that is a product term. So, a single term is also a product term, remember, AB plus C. So, these both are product terms, connecting that with plus is okay. So, by definition single literals are sum of products, because there is no product there, no sum there, single literals have to be sum of products. This A plus B is also a valid sum of products, because you can think of A as a product of just A, that is it, one variable, one literal, and B is just one. So, it is a summation of product A and product B. So, if you understand that A itself is a valid product term and B itself is a valid product term, A plus B is a valid sum of products. Similarly, a product of sum expression is a set of sum terms or OR terms which are connected with logical OR operator, logical AND operator, I am sorry, this must have been an AND, they are connected with logical AND operator. So, A bar, A plus B plus C, all these are valid product of sum terms. So, if I look at this, A plus B plus C is a valid sum term, it is not multiplied with anything, it is not, there is no product of it with anything else. So, a single term is a valid product. This is a more good example. A bar plus C is a valid sum term, B plus D is a valid sum term, and there is an implied AND between these two. So, A bar plus C and B plus D, so that is a valid product of sum terms. So, this is a product of sum expression. And finally, we get to what is called the canonical sum of products, and this refers to expression which is written in terms of minterms. So, if I go and look at the expression A bar plus C, it is a valid sum of products, right. A bar B is a product, C is a product, A bar B plus C is a valid sum of products. However, in the canonical sum of products, each product should be a minterm. So, in this case A bar BC is a minterm, ABC is a minterm. So, when I combine these two, right, it is a valid canonical sum of product expression. The reason why it is canonical is each of the term has each of the product term is actually a minterm. So, a minterm is one in which it is first of all a normal term, no variable can repeat, and all the variables should appear at least once. So, all the variables are appearing at least once here, all the variables here are appearing at least once here, and there is no variable that is repeated. So, equivalently we have the canonical product of sums, where each of the product, so there is a product between sums, each of the sum term should be a max term. So, this is a max term and this is a max term, so this is a canonical product of sums. So, I am not implying that this expression is actually equivalent to this expression, I did not imply that. This is a different expression, this is a different expression, this is a valid CSOP expression, this is a valid SOP expression, but it is not a CSOP expression. Similarly, this is a valid CPOS or canonical product of sums, this is not a valid canonical product of sums. So, the reason why we have these max terms, min terms, canonical sum of products and all of this mumbo jumbo is because there is a direct correspondence between the truth tables and min terms and max terms. So, let us take a look at DeMorgan's theorem. I showed this in the previous module, x1 plus x2 and so on up to xn, the complement of that is x1 complement and x2 complement and so on. So, what it essentially says is, if I start with a sum of products, so let us say x1 is a product term, instead of individual variables x1, x2 and so on, assume that x1 itself is a product term, x2 itself is a product term and so on. If I take individual product terms and I do a summation of those things, and if I take the complement of that, so the complement of sum of products, So, the complement of sum of products is the product of the complements. So, you can see that each term got complemented. So, complement of sum of products is equivalent to product of complements, and complement of product of sums. So, you have product of, let us say x1 is a sum term, x2 is a sum term, and so on up to xn. If I take the product of those and complement it, it is the same as the summation of the complements. So, this is DeMorgan's theorem actually. So, this is a easier way to put it in English. Complement of sum of products is equivalent to product of sums, product of complements, and complement of product of sums is equivalent to sum of complements. So, let us start with the Minterm again. A Minterm can be defined as a product term that is 1 in exactly one row of the truth table, right. So, now we will take it to truth tables, and usually you go and represent a n variable Minterm using n bit binary integers. Let us see how to get a Minterm with an integer expression. So, how you start with some ordering on the variables and you form a binary number and you follow these two rules. So, they may look like it is a bit complicated, but we will see with examples it will become clear. We will set bit I of the binary number to 1 if the ith variable appears in the Minterm in the uncomplemented form, and we set it to 0 it appears in the complemented form. So, let us look at this 3 variable expression here. This is x bar y bar z bar, x bar y z, x y z. It is a function on 3 variables x, y and z. So, can you tell me whether this is a valid sum of product expression? Just take a while and think about whether it is a valid sum of product expression. So, if you think about it, is it, so there is a sum separating 3 terms and each of these terms is a product. So, it is a valid sum of product expression. So, if I ask you this question, is it a valid canonical sum of products? The answer would be true for that also, because this is a function on 3 variables. In a canonical sum of products, each of the terms, each of the product terms cannot have any repetitions and all the variables must appear. So, this term has xyz, this term has xyz, and so is this term. All of them have xyz in some form, in either the complemented or uncomplemented form. All the literals xyz are available. So, this is a valid canonical sum of product. The way we are going to write this is as follows. So, if we take x bar, y bar, z bar, we assume that the ordering is x, y and z. Wherever I see x in the complemented form, I will put a 0. Wherever I see x in the uncomplemented form, I will put a 1. So, if I take this product term x bar, y bar, z bar, right, it is actually the Minterm 0, 0, 0. The reason is x is appearing in the complemented form, y is appearing in the complemented form, and z is appearing in the complemented form. We assume that the ordering is x, y and z from the left to right. So, this 0 means x is complemented, this 0 means y is complemented, and this 0 means z is complemented, and a Minterm with 0, 0, 0 means that we have the AND of x complement, y complement and z complement. Let us try and interpret this one. X should be in complemented form, y should be in regular form and z should be in regular form, and it is a Minterm, which means it is a product of these 3 literals x bar, y and z. That is what we have here. Finally, the last one has all of the literals in their uncomplemented version, so it is x, y, z. So, the way we will use this is, we will call this term M000 term, we will call this term as M011 term, and we will call this term as M111 term, right. So, wherever it is complement you put a 0, wherever it is not complement you put a 1. So, this is 000 term, this is 011 term, and this is 111 term. That is what we have here. So, this is in the binary form. If you take this into equivalent decimal expression, this 000 is actually decimal 0, 011 is decimal 3 and 111 is decimal 7. So, one concise way in which we can write this expression f of x y z is to write it as the Minterm M0 or the Minterm M3 or the Minterm M7, which is the same as, we will use sigma notation to say that it is sum. We know that for regular algebra, right. Whenever we have sum of different things, we can put a sigma outside So sigma of m naught comma m3 comma m7. So you can see that it's a comma separating these three. You can think of it as a set of terms m naught, m3 and m7, and you have to logically OR those things. That's what the sigma implies. And this m3, m naught, m3 and m7, it's all in subscript form, and we can drop this whenever we know that it's a sigma outside. We can just drop the small case m and just write it as 037. So if you see a sigma of 037, it means it's the sum of minterm 0, minterm 3 and minterm 7. And minterm 0, as if I give you the variable ordering x, y, z, minterm 0 would be x bar, y bar, z bar. Minterm 3 would be x bar, y and z, and so on. Let us see the max terms. A max term can be defined as a sum term that is 0 in exactly one row of the truth table. So if I give you a truth table, I go and look at one of the ones or 0. So I go and look at the output column. Wherever there is a 0, the corresponding term is what I am going to look at. So the n variable max terms are represented by binary numbers, as I showed earlier for minterms, and this is the way we get the max terms is slightly different from the way we get the minterms. So we state an ordering of the variables. The last example we had x, y, z. We form a binary number by concatenating several things. We will set bit I of the binary number to 0 if the ith variable is in uncomplemented form, and we set it to 1 if it is in the complemented form. So this was the reverse of what we did for minterm. So let us look at the example here. If I go and look at these three things, it looks like it's a valid product of sums. Each one of them is a sum and it's a product of sums. In fact, it's a valid canonical product of sum expression because each of these things is a valid max term. So a max term is one in which all the variables appear either in the complemented or the uncomplemented form. So we have x plus y plus z, x plus y plus z bar and x bar plus y plus z. If I want to find out this expression, if I want to write this expression in a slightly simpler manner, we want to define the notion of max terms. So we have x or y or z. What we are going to do is whenever a variable, so first of all we stick to the ordering x, y, z, we cannot change the ordering, right, x, y, z. If I give you x, y, z here, the interpretation for this 0 is attached with z, x, this is with y and this is with z. So x is in the uncomplemented form. For max terms we will put 0, this is in the uncomplemented form, so again we put a 0, this is in the uncomplemented form, again we put a 0. So this corresponds to the max term 0, 0, 0, and as a shortcut notation we use capital M to say max term and small case m for minterms. So this capital M says it's a max term 0, 0, 0, and again this binary number we use m0 as a shortcut. So this is an integer 0 which is actually for 0, 0, 0. So let us look at this one which is slightly more interesting. So x plus y plus z bar, x is appearing in the uncomplemented form, we associate this bit 0 for that. This is y in the uncomplemented form, so we associate 0 for that, and z bar we associate 1 for that because it is in the complemented form. So max term 001, the shortcut notation we will use is capital M subscript 001, which is the same as capital M integer 1. So this expression is the product of m0, m1 and m4. That is what we have here, x plus y plus z into x plus y plus z bar into x bar plus y plus z is the product of m0, m1 and m4. And again from algebra we usually use pi for product, we use sigma for sum and pi for product. So we will use pi for pi of m0 comma m1 comma m4. So remember there is no AND anymore because pi already implies that we are ANDing. So it is a comma separated list. So it is the product of max term 0, max term 1 and max term 4, and whenever we have a pi implicitly we assume that the terms inside are already max terms. So we can drop the capital M and write it as 014. So it is wrong to write pi of small case m0 and things like that. So we always associate pi with max terms and we associate sigma with min terms. So whenever we write something like 014 here, it assumes that we are already having a capital M, an implied max term which is being multiplied with each other. So let us look at a quick summary. This slide shows you a quick summary of minterms and maxterms. So if I have x1, x2, x3 and if I fix the ordering from left to right, these are the possible choices for x1, x2, x3. You can see that this is number 0, number 1, 2, 3, 4, 5, 6, 7 and so on. So usually in the Boolean world we start numbering from 0. So this is row number 0, this is row number 1 and so on. The row number is actually the integer representation of the x1, x2, x3 in the binary form. So if I take this binary number as 0, 0, 0, its integer form is 0. If I take 1, 0, 0, it's 1 into 2 squared plus 0 into 2 power 0 plus 0 into 2 power, 0 into 2 power 1 plus 0 into 2 power 0, that is 4 and so on. Right. So the associated minterm, if I want m naught, so the is actually x1 bar, x2 bar, x3 bar. If I want max term m naught, that is x1 plus x2 plus x3, because remember on the 3 variables, if I have m naught, m subscript 0 here, like here, it's m 0, 0, 0. So 0, 0, 0 means x1 should appear in the complemented form, x2 should appear in the complemented form, x3 should also appear in the complemented form, and we need a product of these 3. That is what a minterm means. Let us pick this row. If I want small case m4, that is the minterm 4. Minterm 4 would be, I want x1 in the uncomplemented form, x2 in the complemented form and x3 in the complemented form. So that is what you have here, and we have a product of those. If I want capital M4, I look at the row and then I do this. So capital M4 is M1000. So the interpretation for M100, capital M100 is, this one means x1 should be in the complemented form for max terms. So you have x1 complement, and x2 should be in the uncomplemented form and x3 should be in the uncomplemented form. So we have those two, and then max term is a sum term, so you put plus. So this is a quick summary of minterms and max terms. So let us look at this simple expression here. If I have this expression 0, 1, 2, 3, 4, 5, 6, 7, x1, x2, x3 are the 3 variables, the row numbers are 0 to 7, and I look at this function f of x1, x2, x3. We have 8 terms here. If I wanted to go and write it in terms of product terms or sum terms, there is a nice and simple way to do it. So for sum terms, remember, it's you go and look at all the ones. So there is row number 1 which has a 1, row number 4 which has a 1, row number 5 which has a 1, and row number 6 which has a 1. So what we are going to write is f of x1, x2, x3 is, take the rows in which you have them as ones. Row number 1 has a 1, row number 4 has a 1, row number 5 has a 1, and row number 6 has a 1, and we pick the corresponding minterms and add them up or put a logical OR of those. So that is the sigma of m1, m4, m5, m6, and I told you that whenever there is a sigma and a small case m, you can implicitly drop m there. So it is the sum of the row 1, row 4, row 5 and row 6. The English way of explaining this is, f is a function which is on when the condition in row 1 is true, or row 4 is true, or row 5 is true and row 6 is true, right. So one of these conditions should be true, and when is this row 1 will be true? Row 1 will be true if x1 is 0, x2 is 0 and x3 is 1. So that's when row 1 will be exercised and so on. Similarly, if I want to write this as a POS form, a canonical product of sum, in fact, what I do is you collect all the zeros. The zeros are in row number 0, row number 3, row number 2 and row number 7. So you collect all the zeros, so they are in row number 0, 2, 3 and 7, and you put a pi, which implies you are actually taking these as max terms first, and then you are actually doing a product of the max terms, and since pi goes with capital M, you can silently drop the M, capital M, and you have it as pi of 0, 2, 3, 7. So given a truth table, you can write in canonical sum of product using this sigma notation, and canonical product of sum using the pi notation. So this brings me to the end of module 4. In the next module, what we will do is we will try and rewrite various sum of products and product of sums and so on in various different formats, so that all these definitions that I gave you, they should stick in your mind. So I will do that in the next module. So thank you.